Okay, so this one is actually stated in the new, okay, this one is actually stated in the syllabus like this: law of motion, applications of Newton's law, force of friction, equilibrium, and connected objects. So today we are going to, we cannot reach even the frictional force, right? So probably I show you some application of the Newton's third law, right? Earlier on is the Newton's first law and second law, right? Now we look at third law. Can you read this Newton's third law, this one?
Forces in nature always exist in pair. The nail is driven into the block by the force exerted by the hammer. The hammer is slowed down and stopped by the force exerted by the nail. If object 1 and object 2 interact, the force F12 exerted by object 1 and object 2 is equal on the magnitude but opposite in direction due to the force F21 exerted by object 2 on object 1.
Okay, so we look at the hammer, right? Let's say the hammer exert a force of, I cannot see the letter there. Can you see the letter H? Is it HN? HN, I think. Okay. Oh, HN. Okay. Hammer. Hammer and
FHN.
nail, correct. So the force exerted by the hammer on the nail, HN, they exert, because when I swing the hammer, I hit against the nail, the hammer is exerting a force of Hn on the nail, right? Now, of course, the nail will move inside, but actually, the nail also offer a resistance of Hn back on the hammer. That's why the hammer stopped. So in this case, the force exerted by the hammer is called the action. The force exerted by the nail on the hammer, back on the hammer, is the reaction. So actually, Newton's third law says the action and reaction, they are equal and opposite. So if let's say the hammer knock against the nail offer a resistance to the hammer. The magnitude of these two forces are the same. Only difference is the direction. Okay. So hammer exert a force on the nail also exert a force on the hammer. That's why the hammer come to a stop. After hitting the nail, it comes to a stop because the nail also offer equal and opposite force. That's why the hammer stop. So this is the Newton's third law. Over here, in general, we are talking about not specific case, but we are talking about in general. If there are two objects, let's say two objects, this one, gray color object 1, golden color object 2. When they interact with one another means one knocking against the other. Which one knock against you, it doesn't matter, right? When one knock against the other, the force exerted by the first object on the second object, F12, is equal and opposite direction to the force F21 exerted by object 2 on object 1. So if object 1 exert a force on object 2, object 2 also exert a force with the same magnitude but in the opposite direction onto the object 1. So don't think that, oh, let's say you hit someone, you don't feel the pain. Okay, you hit someone, that object also exert back a force on you. You also feel the pain. Okay, so this is Newton's third law. We look at a monitor or a TV resting on the table. Okay, so this object is resting on the table. Now, because this object is not moving up or down, the net force is zero. The force exerted by the object, this monitor, on the table is Fg. The table also provides a support for the monitor in the form of reaction, and we call it N, small n. Actually, it's the normal reaction. We call it the normal reaction. Normal reaction because it is normal to the surface, normal to the surface. Now, in this case, the surface is the surface of the table. Okay, the surface is the surface of the table. Okay, and if we look at the monitor alone, we just look at the object alone, there are two forces acting on this object. One is the normal reaction, the other one is the weight of the object. So the normal reaction is denoted by N. The weight of the object is denoted by Fg. So when you move the N over to the other side, the Fg is equals to negative N. It means to say that the force is in the opposite direction to the normal reaction, or the normal reaction is in the opposite direction to the force, and they are equal in magnitude. That means the size of the force is the same. This one is quite simple. The upward force and downward force, they're the same, right? The weight and the normal reaction, they are the same. So we look at the next one. You read this problem and see. A man of mass.
Man of mass M equals 75 kg and a woman of mass M equals 55 kg stands facing each other on an ice rink, both wearing ice skates. The woman pushes the man with a horizontal force of F equal 85 Newton in a positive x direction. Assume the ice is frictionless. What is the man's acceleration? What is the reaction force acting on the woman? Calculate the woman's acceleration.
Okay, so the question is like this. There's a woman on the left hand side. Her mass is 55 kg. There's a man on the right hand side. His mass is 75 kg, right? So both of them, they are standing still facing one another on. Okay, now why must they say is on the ice skating rink? Because there will not be any friction, or almost zero, the friction between the man and the floor and the woman and the floor. So they give you the ideal case. So the most ideal case where there is no friction is this one. Both of them standing on ice. Actually supposed to be blade, not roller lah. This roller is just the skating, not the ice skating. Okay, let's not worry too much about this. You just replace it with the blade lah. The roller you just replace with the blade. Okay, so what they are trying to say is that there is no frictional force between the people, the two person and the floor. There's no frictional force. So before anything happened, the situation is like this: 55 kg, 75 kg, both of them standing at rest inside a skating ring, no friction. Now, suddenly, this woman pushed the man with a force of 85 Newton in the positive x direction. So this woman exert a force of 85 Newton on the man in the positive x direction. Positive x direction means towards the left hand side. So this woman pushed the man to the right hand side with a force of 85 newtons. and the man is not doing anything. But according to Newton's third law of motion, when you push someone with 85 Newton, you are actually receiving a reaction of 85 Newtons in the opposite direction. So I label here, the reaction is 85 Newtons, but in the opposite direction. So this is actually Newton's third law of motion. The action is F, the reaction is R. Okay, right. Okay, so we are going to use the Newton's second law, which state that F equals to ma. And we apply this formula, F equals to ma, on the man. So the force is 85 Newton, the mass is 75 kilogram, and how much is the acceleration? So acceleration is 85 divided by 75. So it is 1.33 meter per second square. I'll note that this is a positive number. So that means the man will accelerate in the positive direction. What is the reaction force acting on the woman? So because the the woman exert 85 Newton on the man, she will receive a reaction of 85 Newtons, but in the opposite direction. So can you use the equation F equals to ma to find out the acceleration of the woman? Can you find what is the acceleration of the woman using F equals to ma?
We just do 85 divided by negative 55.
Correct. How much is that?
Negative 1.545, so negative 1.55.
Okay, correct. Negative 1.55 means the woman is accelerating in the opposite direction. That's why it is negative, right? Negative 1.55. Okay, there is in the textbook they give a similar. They give you one example, then they give you a similar exercise. So the similar exercise is like this. You read 4.5.
A spacewalking astronaut of total mass 148 kg exerts a force of 265 Newton on a free-floating satellite of mass 635 kg, pushing it in the positive x direction. What is the reaction force exerted by the satellite on the astronaut? Calculate the acceleration of the astronaut and the satellite.
So is it the same as what we have done in the first problem here? Right. Now, instead of having a man and a woman, we are now having an astronaut and a satellite. Instead of 55 kilogram and 75 kilogram, we are having 184 kilogram, 635 kilogram. So it's the same problem. The only difference is that the mass, they are different. Another thing is why they must say in outer space, in the outer space or spacewalking, because up there will be no friction, right? There will be no friction, similar to this skating rink. So there will be no friction. So now the man will give the satellite a push. Okay, how much force? 265 newtons. So can you answer the three questions? Okay, the first question is, what is the reaction force exerted by the satellite on the astronaut. The man exert a force of 265 Newton on the,
265 Newton.
yeah, it will be negative 265. Okay, so if the man exert 265 on the satellite will exert negative 265 on the man. Calculate the acceleration of the astronaut. If you want to calculate the acceleration of the astronaut, you use F equals to ma. So can you use this on the astronaut? Tell me. F equals to ma. The example is on the left hand side. You can refer to the example on the left.
Two, 265 divided by negative 148.
265 divided by 148, not 1.48, 148.
265 divided by negative 148.
Ah, correct. Negative 148. How much is that?
Negative 1.79.
Correct. Negative 1.79. There's a negative sign here. Okay. Next one. What is the acceleration of the satellite?
265 divided by 635.
The other way around. 265 divided by 635. Positive or negative?
Positive.
Positive. How much is it, answer?
0.41.
0.417. Right? So very simple. This is what they meant by this application of Newton's law. Right?